So an NMR spectrum, right, it is actually a plot. In y-axis, we plot intensity. In y-axis, we plot intensity. In x-axis, from left to right, we plot what is called magnetic field strength. Okay, let me write here. Magnetic field strength Bz or B0, which we plot from left to right. So keep this in mind. From left to right, magnetic field strength increase. Okay. From right to left, chemical shift value. Chemical shift value increases from right to left. Actually, for TMS, tetra-methyl-silane, for TMS, we give chemical shift value as 0. Then most of the other signals observe in the downfield. Downfield means the field, the lower magnetic field is called downfield. Higher magnetic field is called high field. So most of the protons occur below TMS. Okay, downfield. Right? Then frequency. Listen carefully. While plotting NMR spectrum, there are two ways. Okay, there are two ways by which we plot NMR spectrum. One is called frequency sweep method. Frequency sweep method. The other one is called field sweep method. Okay. When you plot intensity versus field strength, external magnetic field strength, it is called field sweep method. If you plot intensity versus frequency of the radio frequency radiation, then it is called frequency sweep method. For frequency, we plot frequency from right to left. Observe carefully, chemical shift and frequency we plot from right to left. Okay, for TMS, we take the frequency as 0. Okay, right? Our TMS frequency is nothing but spectrometer frequency in the other way we can say, right? Yeah. So we plot intensity in y-axis and frequency or chemical shift, frequency or magnetic field strength in the x-axis. If we plot magnetic field strength, it is called field sweep method. If we plot frequency of radio frequency radiation, right, it is called frequency sweep method. Okay. Calculate the chemical shift of an absorption that occurs 1500 Hz downfield from TMS. See, 1500 Hz, it is given in Hz, which means frequency is given. Okay, frequency which for particular absorption, frequency is observed in the downfield from TMS. Downfield means lower magnetic field. Using a 300 MHz NMR spectrometer, we need to calculate the chemical shift. Okay, it's very simple. Chemical shift is nothing but from TMS, okay, to what frequency the absorption occurs. Okay, so it is the frequency of absorption, frequency in Hertz. Okay, frequency of absorption occur from TMS. Okay, frequency of absorption occurs from TMS divided by spectrometer frequency. Listen carefully, numerator should be in Hertz and denominator should be in megahertz. So that you need not multiply by 10 power 6. That's the meaning. Now listen, so from TMS, the signal is appeared at 1500 Hz downfield. Okay, frequency of absorption occurs downfield. Let me use that word also. Downfield from TMS, right? So what frequency? it occurs from TMS? It occurs from TMS in the downfield of 1500 Hz. Divided by spectrometer frequency is given 300 megahertz. It should be in megahertz. Okay. Now 1500 by 300. Yes, we'll get. How much we'll get? So the answer is 5 ppm. I have already told you chemical shift is independent of chemical shift in ppm. If we give chemical shift in ppm, it is independent. It is independent of external magnetic field strength Bz. Okay. If we change the external magnetic field, chemical shift does not change. Right? Keep this in mind. See, now what is actually given? What is given? See, we have a TMS signal, TMS. For TMS, chemical shift value is 0. From TMS, we get a signal at 2 ppm. At 2 ppm. Now, from this TMS, at what frequency this signal appears? In the downfield. Right? The downfield, at what frequency this signal appears? If we use 300 megahertz spectrometer. Okay? So, first I'll do this problem. In 300 megahertz spectrometer, observe carefully, right? How to find the frequency? Very simple. Just multiply the chemical shift value right here. Okay. So if you want frequency in hertz, multiply the chemical shift value by the spectrometer frequency in megahertz. Okay. Spectrometer frequency in megahertz you have to multiply. Okay. So this is 2 ppm. This is 300 megahertz. So 300 into 2, I'll get 600 hertz. So the signal at 2 ppm, in chemical shift it is 2 ppm. The signal at 2 ppm, right? What is the frequency for that signal? What is the frequency for that signal from TMS if I use 300 megahertz spectrometer? Yes, the signal will appear 600 hertz downfield from the TMS signal. Is this clear? So in 500 megahertz spectrometer, very simple, the frequency in hertz is equal to chemical shift value, which is 2 ppm, into spectrometer frequency in megahertz, it is 500. So 500 into 2, I'll get 1000 hertz. This is very, very important. Keep this in mind. If you use, listen, this is 300 megahertz instrument, whereas this is 500 megahertz spectrometer. Okay. If we use high frequency spectrometer, we get large separation between TMS and the signal. Okay. Suppose if two signal appears very closely, listen, suppose if two signals appear very closely, right, in 100 megahertz instrument. Suppose if we use, say for example, 500 megahertz instrument or spectrometer, then the gap between the two signals will increase. Okay. So keep this point in mind, right? If you use high frequency spectrometer, okay, you will get more separation between lines, signals, right? So the analysis will be easier, okay, and we can very easily predict the nature of the signal and informations from the signal we can get clearly, right? Go through this question. If two signals differ by 2 ppm in a 300 megahertz spectrum, by how much do they differ in a 500 megahertz spectrometer? This is what I told you. Okay, see what I said here, what is given here. See, if I use 300 megahertz spectrometer, we get two signals, and the gap between the two signals is just 2 ppm. It is given like that. Now instead of 300 megahertz, if I use 500 megahertz, what will happen? Listen carefully. This is actually, the value is given in ppm, right? If the value is given in ppm, then it is independent of spectrometer frequency. Observe this carefully. Listen, if the value, if the chemical shift value, it is given in chemical shift. If the chemical shift value or the gap between two signals, if the gap between two signals is given in ppm unit, ppm value, then that gap is independent of the spectrometer frequency, whether you use 300 megahertz or 500 megahertz. Okay, the gap between the two signals remains 2 ppm only. It does not change. But the frequency will change. Listen carefully. Frequency between the two signals will change, but the ppm value remains the same. That's the meaning. Listen, value given in value, right? Given in ppm, it is independent of spectrometer frequency. What is meant by this? Whether you use 300 megahertz instrument or 500, okay, the gap between the two signals remains 2 ppm. It does not change, but the frequency will change. Okay, we'll see that in the next problem. Right? Yes, go through this problem. If two signals differ by 90 hertz, see, now it is given in frequency. Okay, now we have two signals. From TMS, we get two signals. The gap between the two signals is given as 90 hertz now. Okay, we get 90 hertz in a 300 megahertz spectrometer. By how much do they differ in a 500 megahertz spectrometer? Observe carefully. If the gap between two signals is given in hertz, in frequency unit, yes, it depends on the spectrometer frequency. So what to do? First, you convert this into in 300 megahertz spectrometer, the gap is 90 hertz. Instead of 300, if you use 500, what will happen to the gap? Okay, what to do? Yes, what to do? First, to find the chemical shift. Chemical shift is equal to, listen, 90, that's the gap between the two, 90 hertz, divided by, it is not chemical shift, I am finding the gap. Okay, it's not gap. Right? Gap in, I'm finding the gap. So 90 hertz divided by 300 megahertz. Right? So we get a value of 90 by 30, 0, 0 cancel. So I'll get 9 by 30. So 3 by, 0.3 ppm. We get the value as 0.3 ppm. Now, if I use 500 megahertz, what to do? Multiply this value with the chemical shift value. You will get the frequency in 500 megahertz spectrometer. Observe carefully. If the gap is 90 hertz in 300 megahertz instrument, okay, the value of the gap in ppm is 0.3 ppm. This 90 hertz is equal to 0.3 ppm. Okay. Now, if I use 500 megahertz instrument, we get the two signals. And the gap between the two signals remains as 0.3 ppm. ppm value does not change. But now, what is the gap in frequency? If you want the gap in frequency, what to do? Multiply this gap in ppm with the spectrometer frequency in megahertz. So 0.3 into 500, I'll get 150 hertz. Okay. If you want frequency in hertz, right? Multiply the value of ppm into spectrometer. This is ppm value and this is in megahertz. If you multiply, you will get the answer in hertz directly. Okay. What does it imply? In 300 megahertz instrument, if the gap between the two signal is 90 hertz, then if you run if you take the NMR spectrum of the same compound, right? In 500 megahertz instrument, the gap between the two signal will increase. Okay, right? What is the gap? Now the gap is actually 150 hertz. But remember, the the gap value in ppm that remains same. Okay. Yeah. So our next goal is to find number of signals for a given compound in proton NMR spectrum. If a compound is given, how many signals we get? Okay. See, number of signals is equal to number of different types of protons present in a compound. Protons in a compound. Okay, this is very, very important. Next point, equivalent protons gives same NMR signal. If you have equivalent protons, they give one signal. How to find whether they are equivalent or not? Equivalent or non-equivalent? Yes, we'll see some examples. Okay, now I have given a few examples here. I'm going to show you how to find the number of signals. Okay, now see this compound. How to find whether the protons attached with this carbon and the protons attached with this carbon are equivalent or non-equivalent? Very simple. We have substitution method. Right? What is substitution method? Remove one hydrogen from this and put a chlorine. Okay. So what we get? Cl, CH2, CH3. Can you tell me what's the name of this compound? IUPAC's name? It is 1-chloroethane. Suppose if I remove this hydrogen by 1 chlorine, we get a compound like this, correct? Now name this compound. Name the second compound. So by substitution method, I am getting same IUPAC's name for the two compounds, for the two methyl protons, which indicates that the two methyl protons are equivalent. So we have 6 protons, all the 6 protons, so we have totally 6 protons, all the 6 protons will give only one signal. Okay, so for ethane, we get one signal in NMR because all the protons are equivalent. Right? Now, see this compound. Listen, how many different types of protons we have. Listen, suppose I'll take this methyl and this methyl. If I replace this one hydrogen from this methyl by a chlorine, what will be the IUPAC's name of that compound?
Chlorobutane.
Very good. You'll get 1-chlorobutane. If I replace this hydrogen by 1 chlorine,
The same 1-chlorobutane.
Therefore, see, these two protons are equivalent. If I say this proton is A, this proton is also A because I am getting same name. Now, what about these two? See, if I remove this hydrogen by 1 chlorine, what is the IUPAC's name we get? If I replace
2-chlorobutane.
you will get 2-chlorobutane. Instead of this, you replace one hydrogen from this CH2 and put a chlorine. What's the name? We get the same name. So these two protons are also equivalent. Okay. So I have A protons and B protons. I have only 2 different types of proton. Therefore, this compound, listen, I have 2 different types of proton. So this compound will give me 2 signals in the NMR spectrum. Okay. Take them. Yes. In dimethyl ether, this methyl group and this methyl group, all the 6 protons are equivalent. Therefore, we get only one signal for this compound. Okay, good. Right. What about this fourth one? How many signals we get? Yeah. Yes. Listen, since chlorine is attached here, so it is called this CH2 and this CH3. These protons are not equivalent. Okay, these protons are not equivalent because of the minus I effect. This carbon gets more effect of inductive effect, whereas this carbon and these protons get less effect of inductive. Therefore, these 2 hydrogens and these 3 hydrogens are not equivalent. So if I say this proton is A, this proton should be B. So we have 2 different types of proton. So we get 2 signals in the NMR spectrum of the compound. Right? Yes. What about the 5th one? In this compound, we have a methyl group here and we have another methyl group here. They are methyl groups, but see the attachment. This methyl is attached to oxygen. whereas this methyl is attached to CH2 group. So they are not equivalent. So if this methyl group, the protons attached to this methyl group, right, if it is given symbol A, then these protons supposed to be, it is different actually, right? They are different. So I'll give a different symbol B. And the protons attached with this carbon, the CH2 protons, they are different. Therefore, these protons should be given symbol C. So we have different types of protons. How many different types? We have 3 different types of protons. So we get 3 signals, okay, in the NMR spectrum of this compound. Okay. Yes, what about the 6th one? Anyone tell me?
2 signals, sir.
Very good, sir. Very good. So, this methyl group is directly connected to oxygen. Whereas these 3 methyl groups are connected to this carbon and that carbon is connected to oxygen. So, this methyl group is in different environment and these 3 methyl groups, right, they are actually equivalent. They are in a different environment. So, we have 2 different types of protons. So, we get 2 signals in the spectrum. Okay. Yes. How many signals we get for this compound? Anyone? Yes. This methyl and this methyl are equivalent. So we get 1 signal. This CH2 and this CH2 are equivalent. We get 1 signal. And we get another signal for this CH2. Okay. Take it. So for this compound, we get 3 signals. Very good. See, by appearance itself, we can very easily distinguish. This ethyl group is attached to carbonyl, whereas this ethyl group is attached to oxygen. Definitely, these 2 ethyl groups are not equivalent. Therefore, this methyl group, if it is A, and this methyl group is in different environment, should be given as B. Right? Then this is C and this is D. So, all the, see, this CH3 proton and this CH2 proton are different. This CH3 and this CH2 protons are different. So, for this compound, we get 4 signals in the NMR spectrum. Okay? Right. Now, yes, tell me now, how many signals we get for this compound? The environment of these 2 hydrogens are same. Therefore, they will give 1 signal. Yes, what about this?
2 signals.
Yes, sir.
Yeah, very good. Here I have chlorine. I'm sorry. Here I have chlorine. Here I have bromine. So this hydrogen is cis to chlorine, whereas this hydrogen is cis to bromine. So these 2 hydrogens, okay, they are non-equivalent. They are non-equivalent. So this hydrogen will give 1 signal and this hydrogen will give another signal. So we get 2 signals for this one. Yes, what about this? Yes. In this compound, this hydrogen is cis to this chlorine. This hydrogen is trans to this chlorine. And this hydrogen is actually geminal hydrogen to the chlorine. All these 3 hydrogens, okay, are in different environment. So they give, each hydrogen will give 1 signal. So we get 3 signals for this compound in proton NMR spectrum. Okay, very good. Now, see these 2 compounds. They are isomers actually, structural isomers, right? Positional isomers, 1 chloropropane and 2 chloropropane. How will you distinguish these 2 compounds using NMR? Yes. So first compound will give, see, because this chlorine is attached to terminal carbon, therefore the electronegativity effect on this carbon are not same. They are different. Directly attached carbon, okay, chlorine directly attached to this carbon. So this carbon gets more inductive effect. Then this carbon gets less inductive effect. This carbon gets very less inductive effect. Therefore, these protons are not equivalent. So this proton, if I say A, and this proton should be different B, and this proton should be different C. So I have 3 different protons, so we get 3 signals, okay, for this compound 1 chloropropane. Whereas for 2 chloropropane, this is 2 chloropropane, these 2 methyl groups, methyl protons, they are equivalent. And this proton is in different environment because chlorine is directly attached here. So this proton is in different environment, so we get 2 signals for this. So by just observing the number of signals, we can distinguish 1 chloropropane and 2 chloropropane. Clear? Yes. How many signals we get for cyclopropane? Anyone? Yes. For this compound, we get only 1 signal, right? See, actually speaking, in this compound, see, observe carefully. We have 3 hydrogens above the plane and 3 hydrogens below the plane, correct? But listen, all the 3 hydrogen above and all the 3 hydrogen below, they are all in one equivalent. They are all in same environment. All the hydrogens are in same environment. Okay, therefore they are all equivalent, so we get one signal. Now tell me, for this compound, how many signals we get?
3.
Yes, for this compound we get 3 signals. 3 is the correct answer. Why? Listen here, this proton is directly attached to the carbon where chlorine is attached. So this proton is a different environment. And the proton which are above the plane, right, they are directly facing the chlorine. So these 2 protons are in one environment. Whereas the other 2 hydrogen which are below the plane, right, they are facing hydrogen, chlorine, in the downward direction. Right? And their environments are different. So these 2 hydrogens are in different environment and these 2 hydrogens are in different environment. So this will give, these 2 hydrogen will give one signal and the above 2 hydrogen will give one signal. So we get 3 signals for this compound. Right? Is this clear to all? Yes, can anyone tell me how many signals we get for this compound? The chlorine which is present above the plane, from that chlorine, the bottom 2 hydrogen, these 2 hydrogens are in same environment. So if this is C, this is also C. Okay? Then from this chlorine, this hydrogen, see, this hydrogen is in the top side, whereas this hydrogen is in the bottom side. Okay? This distance and this distance are not same. See? So these 2 hydrogens are in different environment. If I say this is D, this should be E. So how many signals we get?
5.
Yes, for this compound we get 5 signals in NMR, proton NMR. Take 2. Yes, let me give a compound. You try to find out how many signals are there. How many signals we get for this compound, right, in the NMR spectrum. Yes, for this compound, how many signals we get? See, for this compound, the groups which are present here and the groups which are present here, they are exactly same. See the attachment. CH2, CO, O, CH2, CH3. Similarly here, CH2, CO, O, CH2, CH3. They are exactly same. Therefore, this part and this part are equivalent. So you need not consider this. Okay, you just consider this one. So here, this CH2 is in, it is connected to carbonyl group. It is in one environment. And this CH2 is attached to oxygen. So this is in different environment. And this methyl group is attached to CH2. This is in different environment. So we get 3 signals in proton NMR spectrum of this compound. Okay, take it. Tell me how many signals we get for this compound in the proton NMR spectrum. Yes.
2. Acidic.
Yes. Now what I am going to do, how many signals we get for homotopic, anisotropy and diastereotopic hydrogens present in a organic compound in the NMR spectrum. Okay. So first we will discuss anisotropic hydrogen. Okay, what is anisotropic hydrogen? Suppose you see this compound. In this compound, this carbon is attached with the methyl group, OH group and 2 hydrogen. Okay, suppose if I replace this hydrogen by some group, say for example I take chlorine, I will replace this hydrogen by chlorine. If I replace this hydrogen by chlorine, I will get a chiral molecule. Okay, see this carbon is attached with the 4 different group. So it is a chiral carbon and the molecule is a chiral molecule. Okay, this is actually one enantiomer. If I replace this hydrogen by chlorine, right, what will happen? I will get CH3 group, OH group, and this hydrogen remains as such, but this hydrogen is replaced by chlorine. Okay, now if you find the configuration of these compounds, okay, we will get opposite configurations, right? If I replace this hydrogen by chlorine, I am getting an R isomer. If I replace this hydrogen by chlorine, I will get an S isomer. Okay, R and S isomers of the same compound are called enantiomers, right? R and S isomers of the same compound are called enantiomers. Clear? Therefore, These hydrogens are called enantiotopic hydrogens. Enantiotopic hydrogens. Okay? Listen, if two hydrogens present in a compound, if I replace one hydrogen by some group, if I get R isomer, if I replace another hydrogen attached to the same carbon by a group, if I get S isomer, then we call those hydrogens as enantiotopic hydrogens. Remember, in NMR spectrum, enantiotopic hydrogens are chemically equivalent. Okay, let me write here. Enantiotopic hydrogens are chemically equivalent. They are chemically equivalent, so they'll give one signal in NMR. Enantiotopic hydrogens will give one signal in NMR. Okay. Now our goal is to find whether these two hydrogens are enantiotopic or diastereotopic or homotopic. So what I'm going to do, first I'll find the configuration of this carbon. Okay, this chiral carbon. Okay, yes. Listen, here we have one hydrogen least priority, and bromine here I'll give priority 1, and here we have large groups, I'll give second priority, and methyl third priority. So fourth priority group is in horizontal position. Okay, and 1, 2, 3 going in anti-clockwise direction. Right? Anti-clockwise means usually it is S. Since the least priority group in horizontal, it is R. So this carbon has R configuration. This carbon is R configuration. Now, if you replace this H by a chlorine, what will happen? See here. Observe this carefully. See, the configuration of this carbon is R. It is fixed. Now, what I am going to do? I'll replace this hydrogen, I'll put some chlorine. Okay. Now, what is the configuration of this carbon? Okay, let me do it here. Yeah. So, I have least priority group 4 and chlorine has highest atomic number 1 and bottom group is bigger. So, 2 and this is 3. 1, 2, 3. See, least priority group in horizontal position and 1, 2, 3 is going in anti-clockwise direction. Anti-clockwise means, clockwise means R. Anti-clockwise means it is supposed to be S, but least priority group is in horizontal, therefore this is R. Okay. Now, see what I did here? I replaced the hydrogen HA. I replaced HA hydrogen by chlorine. Now I will replace HB by chlorine. So if I replace HB by chlorine, what will I get? Keep the other groups as such. So this configuration remains R. Now, what I am doing, keep the HCl hydrogen as such, replace this HB by chlorine. HB by chlorine. Now, what is the configuration of this carbon? Tell me. You know how to do that.
Yes, sir.
You will get yes. You will get yes configuration. Now listen carefully. See these two structures. Listen. One configuration is R, but the other configuration, one is R, the other one is S. Okay. In the two compound, one of the configuration remains same, but the other configuration is changing. This means the two are diastereomers. If both configuration changes, suppose this is R and here this is S. If suppose this is R, if this is S here, then they are enantiomers. If both configuration changes, it is enantiomer. But one configuration remains same, only the other configuration is changing, which means they are diastereomers. Therefore, these two hydrogens are diastereotopic hydrogens. Okay, HA and HB, they are diastereotopic hydrogens. And remember, diastereotopic hydrogens are chemically non-equivalent. They are chemically non-equivalent. Very important. So that each one will give one signal in NMR. So we get two signals for this. Okay. Anisotropy hydrogens. If you have two hydrogens which are anisotropy, then each hydrogen will give one signal in the NMR. So we get two signal for these hydrogens. Is this clear to all? Follow. So here, if I replace HA by chlorine, I'll get, if I replace HA by chlorine, I'll get a cis isomer. If I replace HB by chlorine, I'll get, see HB, I'll replace HB by chlorine, I'll get a trans isomer. So HA will give cis isomer, HB will give trans isomer. It means, you know very well, cis and trans isomers are diastereomers. Therefore, these two hydrogens are diastereotropic hydrogens. Diastereotropic hydrogens are chemically non-equivalent. Therefore, this one will give one signal and this hydrogen will give another signal. So we get two signals for these two hydrogens. Okay. So our goal is to find how many signals we get for the indicated hydrogen. Okay. First of all, tell me what's the name of this compound?
Hexene, sir.
Hexane. Very
N-hexane.
good. Now tell me for this CH2, it has two hydrogen. How many signals we get for this CH2? What is homotopic? If two hydrogens on replacement by chlorine, if they neither form enantiomer nor form diastereomers, then the two hydrogens are called homotopic hydrogens. I repeat, if two hydrogens attach to a carbon, if you replace one by chlorine and another by another chlorine, okay, in a subsequent manner, first replace one chlorine and find the isomer, find the configuration, and replace another chlorine, another hydrogen by chlorine, and find the isomer. Suppose if you don't get any enantiomers, if you don't get any diastereomers, then those two hydrogens are called homotopic hydrogens. Okay, homotopic hydrogens are chemically equivalent. Homotopic hydrogens are chemically equivalent, they'll give one signal. Enantiotropic hydrogens are chemically equivalent, they'll give one signal. Whereas diastereotropic hydrogens are chemically non-equivalent, they'll give two signals actually. Right? Now tell me how many signals we get for this CH2 protons. This compound will give only one signal. Why? See, let me write here. See this example. Here I have two hydrogen. So I'll put one hydrogen like this and another hydrogen like this. Okay. Listen, if I replace this hydrogen and if I put chlorine, will this carbon become chiral? You replace this hydrogen and put a chlorine. Will this become,
Yes, sir.
will this carbon become chiral or not? Check it. This
Yes,
side
sir,
I have
chiral, sir.
ethyl group.
Chiral, sir.
Chiral. So it gives you a chiral carbon. It gives a chiral carbon, correct? If I replace this hydrogen by chlorine, yes, I'll get the chiral carbon and I'll get two different isomers. This hydrogen will give maybe R isomer and this replacement of this hydrogen will give S isomer. So these two hydrogens are enantiotropic hydrogens. Am I right? Enantiotropic hydrogens. Enantiotropic hydrogen will give?
One signal.
They are chemically equivalent. They'll give one signal. Okay. Yes. Next one. Tell me how many isomers or how many signals we get in the proton NMR spectrum of this carbon. Yes.
Sure.
See, the hydrogens attached to this carbon, the two hydrogens attached to, see, if I replace one hydrogen by chlorine, will I get chiral carbon or not? If I replace this hydrogen by a chlorine, will I get a chiral carbon or not?
Chiral.
Yes,
Chiral, sir.
we get a chiral carbon. So this hydrogen or this hydrogen, if you replace any one by chlorine, we get a chiral carbon. And if I replace this hydrogen, if I get R isomer, suppose, then the replacement of this hydrogen will give S isomer. Therefore, these two hydrogens are enantiotropic hydrogen, so I will get one signal for this. Okay. Now, I'll give another example. Yes.
Sir,
Yes. Now this is the carbon. Yes. We get two signals for this, for the two hydrogens attached to this carbon. Okay. Why? Listen carefully. The two hydrogens attached here, right? If you replace one hydrogen by chlorine, this carbon become chiral. If you replace this hydrogen by chlorine, you get a chiral carbon. Yes, this carbon become chiral, no doubt. And this carbon is already chiral. See here, adjacent carbon which is already chiral. So if you replace this hydrogen, I will get, suppose if this is R. Okay, if I replace this hydrogen, if I get R, if I replace this hydrogen, I will get, see, one will give RR isomer, RR. The other hydrogen on replacement will give RS isomer. RR, RS. See, one configuration is same, the other configuration is different, which means they are diastereomers. So the two hydrogens are diastereotropic hydrogen. Diastereotropic hydrogens are chemically non-equivalent, so they will give two signals. This hydrogen and this hydrogen, they will give, each one will give one signal, so we will get two signals. Okay. In the same compound, if I give the compound, instead of this carbon, if I give this carbon, tell me how many signals I will get for the two hydrogens attached to this carbon. Yes, the two hydrogens attached to this carbon, it is also diastereotopic, we get two signals. Okay, right, now, see this one. Yes, tell me, these two hydrogens. Right, the next point under this basics of NMR is intensity of signals. Okay, in proton NMR. Right, what decides the intensity of signals? Okay, in NMR, we get one or more signals, right? And what decides the intensity of the signal? Listen carefully. Area under an NMR signal. Suppose if you have a signal, the area under this signal, it is directly proportional to number of absorbing protons. Number of absorbing protons. Very important. Okay, if you get a signal, this signal may be due to one hydrogen, this signal may be due to two hydrogen or three hydrogen or five hydrogen, whatever it is. Okay, the area of that signal, the area under this signal is proportional to number of absorbing protons. Okay, normally listen, when you take NMR spectrum, okay, each signal is given with an integration value, okay, or we can say step. This is called a step. This is called one step, right? So each signal is given an integral or integration value. That integration will give the height of that step. Height of that step, okay, that will be given in the spectrum itself. Okay, the height of each step. See, this is actually called one step. The height of each step, it is proportional to area under the curve. In the spectrum, they will give the height. Height is proportional to area. And you know, your area, it is proportional to the number of absorbing protons. Number of absorbing protons. How many protons absorbs the radiation, gives that signal. Okay. So, instead of area, I am going to take the height. Height is provided. Height will be provided in the spectrum itself. Okay, if height is given, how to find the number of absorbing, or how to find the ratio? Okay, right. Listen carefully. Keep this in mind. If the molecular formula of the compound is given, yes, we can find in each signal how many protons are there. We can find number of protons associated with each signal. We can find if the molecular formula is given. If molecular formula is not given, then I can give only the ratio. Okay, by comparing the two peaks, I can say what is the ratio of protons, okay, that exists and that is responsible for the two peaks. That we can say. Are you able to follow? Just go through this question. A compound of molecular formula C9H10O2 gives three NMR signals having the indicated integration values. Signal A has 54 units. That is the height of the step for signal A. Signal B has 23 units. Signal C has 33 units. The question asked is, how many protons give rise to each signal? What to do? It's very simple. What to do? Listen, the first step is this. First step. Listen, just add the units. For signal A, we have 54 units. For signal B, we have 23 units. For signal C, we have 33 units. Add the three values. What we get? 54 plus 23 plus 33. How much we get? What's the total? Yes? Total is?
110, sir.
110 sir, 110 sir.
110 units, correct? 110 units. So total units is 110. Second step, number of protons. What is the total number of protons available? Total number of protons. See the formula?
10 sir.
Total number of protons available in the compound is 10. Listen, for 10 protons, okay, the total units is 110. Then for 1 proton, what is the unit?
11 sir.
Yes, unit for 1 proton, 1 proton. So what to do? 110 by 10, 110 by 10. So we get
11.
So for each proton, we get 11 units. Note down, note down. Therefore, number of protons in signal A, number of protons in signal A, okay, equal to, how to find how many protons will give signal A? Very simple. See, signal A unit is 54 units, right?
4.9 sir, 5 sir.
Yes, 11 units. So it is roughly 4.9.
9 sir.
4.9. So it is roughly 5. So this signal has 5 protons, right? See, I have given a similar question. A compound of molecular formula C8H14O2 gives 3 NMR signals having the indicated integration values. Signal A 14 units, signal B 12 units, signal C 44 units. How many protons gives rise to each signal? Yes.